Hey guys, in this video we're going to talk about Chapter 13, Section 3, the dot product. Okay, so what is the dot product? Well, basically, the dot product is a way that we can multiply two vectors together with the goal of preserving certain nice properties. So when we multiply vectors together, we don't multiply by components like we do with addition or subtraction. We actually do something different. We basically take the coefficients of the components and multiply them together and then add them all up. Okay, and we're going to do some examples of that. So, if you have, for instance, if you have vector v is equal to v1i plus v2j plus v3k, and w is equal to w1i plus w2j plus w3k, then the dot product between v and w, we're just going to take those coefficients, those corresponding coefficients, multiply them together, so v1 times w1, and then add them all up, right? So then v2 times w2 plus v3 times w3. So that's how we compute the dot product algebraically. Now we can also look at the dot product in a geometric sense. Okay, so that was the first thing that we looked at, was the algebraic definition. Now what about up here, the geometric definition? So this is saying that if we take the dot product of two vectors, what this is going to be equal to is the magnitude of vector v times the magnitude of vector w times the cosine of theta, where theta is the angle between the two vectors. Okay, and so that's the geometric definition, and we're going to do some examples where we use both the geometric definition and the algebraic definition. Now keep in mind, this is very important, the dot product is always a scalar number. So whenever you compute the dot product, you're not going to get a vector, you're just going to get a regular number. Okay, so let's get on with it and do some examples. So we have two vectors in this example. We have vector v and we have vector w, and we want to compute the dot product both algebraically and geometrically. So I'm going to start algebraically because I think that's the easiest. Now algebraically, what we want to do is we want to multiply the corresponding coefficients. So like the x coefficient for v is 1, the x coefficient for w is 2, so we do 1 times 2. Okay, plus now we take the coefficients of the y component. Now since there's no y component here, that's going to have a coefficient of 0. So this is going to be 0 times the coefficient of this y component is 2. And so our dot product is just 2 plus 0 is 2. That's all it is. Notice we got a scalar number. We didn't get a vector. So again, computing the dot product is going to give us a scalar, not a vector. Now let's take a look at this geometrically. So according to our definition, the geometric way to interpret this is the following. The dot product of v and w is going to equal the magnitude of v times the magnitude, and maybe I should leave the dot out just to not get confused with magnitude and multiplication, or multiplication and dotting. Let's just leave that out for now, just so we don't get confused there. My geometric definition says v dot w is equal to the magnitude of v times the magnitude of w times the cosine of the angle between v and w. So we can draw a little picture here to figure out what our dot product is going to be. So since we are in two-dimensional vectors, right, we don't have a k component in either of these. We're in 2D. We have an x and a y, and my vector v is only going out 1 in the x direction. So this is my vector v right here. So this is vector v. And then w is going to have an x component of 2 and also a y component of 2. So we go out 2 units, so this was 1 unit. We go out 2 units to the left, 2 units up, and so our vector is going to terminate approximately right there. So this is going to be vector, this is going to be vector W, okay? And so what our goal is, it's pretty easy to figure out the magnitude of V and W, right? We have a formula for that we can use super easily. What we really need to figure out is what theta is. What is that angle between them? And once we have that, we have everything we need to know. So what we can do here is we can sort of build a right triangle out of the information that we have here. And how I'm gonna do that is I'm just gonna drop an altitude right here, so that I have a nice little right triangle, so I can use my trig properties. And I want to figure out what that angle is. And so, one way I can do it is I can label the adjacent side and the hypotenuse. Right? I can get numbers for those quite easily. Now, what is the base going to be? Well, the base is going to be 2, right? Because we terminate here at x equals 2, so this length, this base, is going to be 2 units long, right? That's including v in it. It's not just v is the base, but it's actually, the base is actually including this piece as well right here. So, this base of the triangle is going to be 2, and the hypotenuse, well, the hypotenuse is going to be, that's going to be the length of W, which is the magnitude. So let's go ahead and maybe rewrite this as the magnitude of W so that we know we're dealing with lengths there. And so to figure that out, the magnitude of W is going to be the square root of the squares of the components, or the coefficients of the components. So notice in W we have 2, and we have 2 as our coefficients. So we're just taking the square root of 2 squared plus 2 squared. And so the magnitude of W, that length of that vector right there, is going to be the square root of 8. Right? And maybe I'll just leave it. I don't have to, worry about simplifying it. So that's the square root of 8. So I'm just going to replace this magnitude of W with the square root of 8. And I'm going to draw this over here so it looks better. So we have theta. We know that this is the square root of 8. We know that this is 2. And since we have an adjacent and a hypotenuse, we can figure out theta pretty easily by saying, well, I know that cosine is adjacent over hypotenuse. So in this case, the cosine of theta is going to be adjacent to over hypotenuse root 8. Now I can use my calculator to take the cosine inverse of 2 over root 8, right? Cosine inverse is going to spit out an angle. And so when I do that, and I make sure that I'm in degree mode, it's going to be 45 degrees. Alright, so theta is equal to 45 degrees. We just figured that out. We just figured out the magnitude of W is equal to root 8. So I'll put that right there. And now we just need to figure out what the magnitude of V is, and we'll have our answer. We'll have V dot W. So the magnitude of V, again, we're just square rooting the squares of the coefficients of V. Now if we go back up to V, we have 1 is my coefficient of x, and 0 is my coefficient of y, even though it's not written there. So all we have is 1 squared plus 0 squared, which of course is just the square root of 1, which is 1. So the magnitude of V is going to be 1, and now we can go ahead and figure this out. So let me do some erasing here, and we can do our computation. Okay, so from the unit circle or from your calculator, if you do the cosine of 45 degrees, that's going to give you root 2 over 2 times root 8 times 1, and that's equal to V dot W. Okay. So if I simplify this, root 8 times root 2 is root 16 over 2. That's going to be 4 over 2, which is 2. So v dot w is equal to 2, and that's the same answer that we got algebraically. So geometrically, it's the exact same thing. And we're going to use both of these ways to figure out different things. So, all right, let's go ahead and just do some examples of using the dot product. So if we're given two vectors with their components, it's the easiest thing to do is to just compute your dot product algebraically. And so what we're going to do is we're just going to multiply our corresponding coefficients. I'm going to do the x's in green, I'm going to do the y's in red, and I'm going to do the z's in purple. You're just multiplying them and adding them together. There's really nothing to it. So v dot w is going to be equal to 1 times 2 x coefficients plus negative 5 times 4 y coefficients plus 3 times negative 8. And then we simplify. So 2 minus 20 minus 24 is going to give us negative 18 minus 24, negative 42. So that is our answer here. That is v dot w. All right, now they're asking for angle. Now, if you're asked to figure out what the angle between vectors is, you want to use a geometric definition because that's where the angle theta shows up. So the geometric definition says that if we do u dot v, we should get the magnitude of u times the magnitude of v times the cosine of theta. Okay, so what can we do? Like, what can we actually get an answer to? Well, we can definitely figure out what this is algebraically. We can definitely figure out what this is by using our square root of squares, right? Actually, maybe this and this. So let's go ahead and do that in our scratch work. So for the scratch work, we're going to first do u dot v. And again, I'm just taking my corresponding coefficients, multiplying them up, and adding them with the other corresponding coefficients. So in this case, I have 3 times 2 plus 2 times negative 1. And that's going to give me 6 minus 2, which is 4. So perfect. We have u dot v is equal to 4. So I'll just replace that right here. Just replacing what I know into my geometric formula for the dot product. Now the magnitude of u, remember we're just taking the square root of the squares of the coefficients in u. So my coefficients are 3 and 2, so we're doing 3 squared plus 2 squared, taking the square root, and I get the square root of 13. So the magnitude of u is equal to the square root of 13, and I'm just going to replace that right here. Okay. Finally, I can figure out the magnitude of v pretty easily, and then I'll be able to solve for theta, which is what I was trying to do all along. I'm trying to find the angle between these two vectors. So the magnitude of v is going to be the square root of the squares of the coefficients. So the coefficients are 2 and negative 1. So 2 squared plus negative 1 squared, and that's going to give us the square root of 5. So that is my magnitude of v. So I'll replace that here. Okay. All right, so that is my scratch work. So I'm going to erase this, and then I'm going to go ahead and solve for theta in my equation above. Okay, so I get 4 is equal to root 65, just multiplying those, times cosine theta. I'm going to go ahead and divide both sides by root 65. And then I'm going to take the inverse, the cosine inverse of 4 over root 65 to get theta. Right? My inverse function is going to spit out the angle for me. So let's go ahead and do that. I'm going to do it in radians just to switch it up on you. Cosine inverse of 4 over square root of 65. And that's going to give us about 1.05 radians. Okay, so that is the angle between the vector u and the vector v. So here's some properties of the dot product that you can write down. So as I was saying, the dot product has these nice properties, and so that's why we define multiplication in this way between two vectors. This one right here is actually really nice because it says that v dot w is the same as w dot v. So the dot product commutes just like regular multiplication does. And then we have, the distributive property, associativity, and then we have v dot v is equal to the magnitude of v squared, which is not too hard to convince yourself of. So maybe try to prove this as an exercise. Can you prove that to yourself, that v dot v is equal to the magnitude of v squared, just using the definition? Okay, let's talk about perpendicular. So when you took geometry, you learned that a perpendicular angle is made with 2 rays. We're going to be calling them vectors here. And between the two vectors is going to be 90 degrees. So that's what perpendicular means. Another word for perpendicular that I'm going to be using sometimes is orthogonal. Okay, so two vectors, v and w, are perpendicular, or another word, orthogonal, if and only if the dot product of those vectors is equal to 0. Now let's consider our standard basis vectors that we talked about last time. We talked about k, j, and I, right? And so another way to indicate perpendicular is with this little symbol right here. What we would say is, we would say k, vector k, is perpendicular to vector j. So this little symbol means perpendicular, and I think you guys have probably seen this before, but if you haven't, that's perpendicular. So k is perpendicular to j. What does that look like on the picture? Well, I mean, it's pretty clear that these guys make a right angle, right? But let's prove that using the dot product. The dot product says that if we do k dot j, we should get 0, right? If it's 0, then they're perpendicular. If it's not, then they're not perpendicular. So k dot j. Well, when I dot, I multiply the corresponding components. So I do 0 times 0, then I add them all up, plus 0 times 1, plus 1 times 0. And indeed, when we take this dot product, we do get 0. So therefore, these 3 dots mean therefore, vector k is perpendicular to vector j. And this is what you should try on your own. Try to prove that not only are those guys perpendicular, but also prove that I is perpendicular to j, and I is also perpendicular to k. So try to prove this using our dot product definition, just like we did here. Okay, which pairs from the following list of 3-dimensional vectors are perpendicular? So how can we figure this out? Well, this just means dot product is 0. That's all we're trying to do here. So we have to check them. So we have to check, is u perpendicular to v? Is vector u perpendicular to vector v? Well, we have to take the dot product and see if it's 0. So the corresponding coefficients are both 1, so we have 1 times 1. Adding to it, well, here we don't have a j, so that's going to be understood to be a 0j times root 3j. And then over here we have a root 3k, but we don't have a k over here, so this is just going to be plus root 3 times 0. And then we can compute. So 1 plus 0 is just 1. So no, not perpendicular, not 0, so not perpendicular. All right, so the dot product would have had to be 0 for that to work. Okay, let's do the next one. Let's see, is it true that v and w are perpendicular? Well, we'll take the dot product again. So my corresponding coefficients for v and w, we have 1 and root 3. Adding to it, root 3 and 1 for the j. Adding to it, 0 for v. 0 is the k component of v, times -1 for w. Alright, so computing this, we get root 3 plus 0. That's 2 root 3, and that's not 0. So these are not perpendicular either. Let's do the last pair. So we did v and w, we did u and v. Let's do u and w. So is it true that u is perpendicular to w? Taking the dot product, we have u, the components, we have the x component is 1 of u. For w, the x component is root 3, plus the y component for u is 0, the y component of w is 1, plus the k component of u is root 3, the k component of w is -1, and indeed we have root 3 plus 0 minus root 3 is indeed equal to 0. So yes, u is perpendicular to w, and we prove that using the dot product. Okay. So let's go ahead and compute the angle between v and w from the previous example. So for this, we need the dot product formula, the geometric one. So the geometric, because we're looking for angles, this is the one that has the angle in it. It's going to tell us that v dot w, so the dot product of these two vectors, is going to be equal to the magnitude of v times the magnitude of w times the cosine of the angle between v and w. Okay? So let me remind myself what v was. Let's see. V is 1i plus root 3j. And then w is going to be root 3i, 1j, -1k. Okay, so those are my vectors. And so what we can easily find here is we can figure out what this is, we can figure out what this is, and then we'll just be left with cosine of theta at the end of the day. So for my scratch work, we already did v dot w, and let's turn and see what that was. So v dot w happened up here, and that was 2 root 3. So this is 2 root 3. Now the magnitude of of v, that's where I'm at next because I already took care of this. The magnitude of v is just going to be the square root of the squares of the components. So we have 1 as a component and root 3 as a component. So we have 1 squared plus root 3 squared. That's going to be the square root of 4, which is 2. Okay. And then we have, I think I did that right, 1 and 3, yeah. And then the magnitude of w is going to be square root of root 3 squared plus 1 squared plus negative 1 squared. Again, I'm just squaring each of these coefficients here. Okay, so magnitude of w, 3, 4, 5, that's root 5. Perfect. So now we have everything we need to know to plug this stuff in and find theta. Okay, so plugging everything into the formula, v dot w is 2 root 3 equals magnitude of v is 2, magnitude of w is root 5. Whoops. And we have cosine of theta. So if we divide both sides by 2 root 5, we get root 3 over root 5 equals cosine theta. And what we can do now is we can take the inverse cosine, so cosine inverse of root 3 over root 5, and I'm going to switch it up again and put it in degrees, but you can do it in radians if you want because I didn't specify here. This is going to give us 39.2 degrees, so this is theta. So since we've been talking about vectors, and specifically perpendicular vectors, now is the time to bring back planes and talk about normal vectors to a plane. So what does that mean? So a normal vector to a plane is a vector that is perpendicular to the plane, and so what that means is it's perpendicular to every displacement vector between any 2 points on the plane. So, if you have a displacement vector on this plane that looks something like this, all we do is shift the normal vector over so that it is perpendicular to this displacement vector. So, before we talked about planes in the sense of them having slopes in the x and the y direction, so now what I want to do is I want to talk about planes in terms of vectors and how the normal vector in particular influences the plane's direction. Okay, so the normal vector, again, it's just a vector that goes straight up. So like imagine if you have a sheet of paper and you're rotating it around, the normal vector, you can think of n as pointing north. That might help you remember this better. But that normal vector is always going to be pointing straight out of the paper, and it's going to make this 90-degree angle with any other displacement vector on the plane. Okay, so excuse me, we have our normal vector, and it has 3 components in 3 space and 3D. So we have AI, BJ, and CK, where A, B, and C are going to be our coefficients. And then what we can imagine here is that with this plane, we have a fixed point, okay? So this point just stays fixed, x naught, y naught, z naught. And then this point right here, x, y, z, is the plane that, or is the point that, that basically moves around and traces out the shape of the plane. So imagine this right here, this little piece, as like a swinging door that swings around and around the plane. And so what you're going to end up having is a picture that looks something like this, right? So here's our normal vector up here. And then you can imagine that this displacement vector is just kind of sweeping out the picture of the plane there. What else did I want to say here? I think that was it, actually. Okay, so the equation of the plane with normal vector, this is a very important little form right there. So the normal vector n is equal to ai plus bj plus ck, and it contains the fixed point p naught equals x naught, y naught, z naught, and then the point that varies, x, y, z. So the equation of the plane is in this form. This is kind of similar to point-slope form in 2 dimensions. We're not going to be using this form a ton, but it's good to know. So that's one form of the plane. And now what's really useful is the fact that we can say that D is equal to, you're basically taking the dot product of the normal vector and the point p naught, and that's going to be our coefficient D in this form of the plane. So this is going to be this form right here is going to be the most useful for us. But of course, this one is also a good one. So again, this is the equation of a plane, as is this. So 2 ways of writing the same kind of idea here. Okay, so some facts before we start solving problems here. First fact is parallel planes have parallel normal vectors. Now again, parallel just means scalar multiple. It means we're scaling a line, right? So again, parallel means same direction is parallel. So like in this picture right here, we have parallel planes, right? Because they're sort of headed in the same direction. They're not gonna, let's see. Yeah, so we have this guy right here. Let's outline it a little bit better. There's our parallel planes in the same direction. And the normal vectors are going to be parallel. So this guy right here is a normal vector that goes through both of the parallel planes. We could also have a normal vector that goes through this guy right here. And so the corresponding parallel vector that would go with the bottom plane could be something like this. Okay, so that's the big idea here, is that parallel planes have parallel normal vectors. In a similar way, perpendicular planes have perpendicular normal vectors, as you might expect. So here are 2 perpendicular planes. They cross each other at right angles, as you can see there. And so if we think about the normal vectors for, let's see, plane Q. So plane Q is going to have, and maybe I'll do this actually let's do it in yellow. So here's my plane Q, and plane Q's normal vector is right here. You can see that it's kind of poking out, so this is going to be the normal vector of Q. Normal vector of Q. And then the normal vector of P, so P is going to have, if you imagine this plane P kind of rotated 90 degrees, you can see that the normal vector that's going to be sticking up on P is going to be this guy that jets out of P. So this is going to be the normal of P, and we can see that these 2 vectors are indeed perpendicular. So parallel planes have parallel normal vectors, perpendicular planes have perpendicular normal vectors. Okay. Let's do some applications of these facts. So which of the following planes are parallel to one another? So going back to the previous slide, we have that our form of our normal vector is going to be AI plus BJ plus CK. And D doesn't really matter, right? Because here we have an equation of a plane. We have A is equal to 2, we have B is -5, C is 3, and D is 9, but we don't really need to worry about D here, okay? So here we could say that a normal vector to this guy, just by using A, B, C, and D and plugging them into this basic form up here, we could say a normal vector to that guy is going to be 2I minus 5j plus 3k. Okay, so this is a normal vector to that first plane right there. Now, let's look at our second plane. We have A is 4, B is negative 10, C is 6, and D is 18. But again, D really doesn't matter when we're writing the form of a normal vector. So our normal vector is going to be A, which is 4I, plus B, which is negative 10. So I'll just write negative 10J plus 6K. So that's a normal vector there. And finally, let's look at our last one here. We have A is 3, B is negative 8, and C is 1. So a normal vector here is 3I minus 8j plus 1k. And guys, I encourage you, I'm not going to do it just for the sake of time, but I encourage you to check these out. So put in these equations in GeoGebra so you can get a really nice visual of what's happening here. You should see that when you plug in these normal vectors and you plug in these planes, they are indeed going to be perpendicular for any vector that lies on the plane. Okay, so we have 3 normal vectors, and the question is, are any of these normal vectors parallel to the others? So the question that we're trying to answer, because if the normal vectors are parallel, then the associated planes are parallel. So which normal vectors are parallel? What does it mean to be parallel? Well, parallel just means that they're scalar multiples of each other. Right? So if we look at the yellow n, I'm just differentiating these by color, and the green n, we can see that these are parallel because if we multiply the yellow n by 2, so 2 times the yellow n is going to give us the green n. That's what it means to be a scalar multiple. So those guys are scalar multiples, but the red one isn't a scalar multiple of either of the other ones. So these guys are parallel, and hence the planes in A and B are parallel. Okay, so let's talk about perpendicular planes. So remember, planes are perpendicular if their normal vectors are perpendicular to each other. What does it mean for vectors to be perpendicular? It means their dot product is 0. So we want to first prove that these planes are perpendicular to each other. So how do we do that? Well, let's go ahead and figure out what their normal vectors are. I'm going to do this first plane in red, and I'm going to do the second plane in green. So the normal vector for the red guy, well, here A is 7, so we have 7i. B is negative 4, negative 4j. And then C is 9. And again, I'm just using this basic form right here. I'm comparing the A, B, and C in this normal form with the A, B, and C in the plane that I'm given. Okay, just wanted to make that clear there. And of course, D is 20, but that doesn't matter. And maybe a good exercise for you guys is to kind of discover why it doesn't matter. Think about that. That's actually an interesting question. Why does that 20 have nothing to do with the normal vector? Okay. All right, so that is our red normal vector. How about green? So we have 2i minus 3j minus 26 over 9k. So the planes are perpendicular. The planes are perpendicular if the dot product of the normal vectors is 0. Right? If the normal vectors are perpendicular. So let's see if this dot product is 0. So when we do n dot green n, we get, well, 7 times 2. So we have 7 times 2 plus -4 times -3, right? Just multiplying and adding the components, plus 9 times -26 over 9. And we have 14 plus 12 minus 26, right? Because those 9s cancel. And indeed, this is going to give us 0. And therefore, the planes are perpendicular because their normal vectors are perpendicular. Okay, let's do some more problems here. Find the equation of the plane perpendicular to this normal vector and passing through this point right here. So I said that this first equation right here was a little bit useless, but maybe it's not because we have a point x0, y0, z0 that we can plug in there. So let's go ahead and do that. I always forget it. So this is just our basic form for the plane. Now we know that x0, y0, z0 is a point on the plane. So this is x0, y0, z0. And we also know something about a, b, and c based on our normal vector, right? So, so here we know that x0 is 1, y0 is 0, z0 is 4, and also a is going to be -1, right? That's just the coefficient of the x value in the normal vector. B is equal to 3, and C is equal to 2. So if we plug all of this stuff in, we're going to get our equation for the plane. So I guess we can go ahead and do that. We could also use that little trick with the D. So D was basically, we were dotting that x0, y0, z0 with a, b, and c, but I'm just going to do it this way just to be consistent, I guess. Okay, so a is -1. We have x minus x naught plus b times y minus y naught. Y naught. Let's see, 2 times z minus 4 equals 0. Okay, so that's our equation of the plane, and yeah, you can simplify it if you want, but that's good enough for me. Well, actually, let's go ahead and simplify it just to make it look like our form down here. ax plus by plus cz equals d. Okay, so let's simplify. We have negative x plus 1 plus 3y plus 2z minus 8 equals 0. Just foiling this and combining like terms and all that stuff. All that fun stuff. So let's see. I get negative x, positive 3y, positive 2z, negative 8 and 1 is negative 7. Add it to the other side and get 7 as d. Okay? So we have, this is the equation of our plane in the form that we were used to. Okay, now it's saying find a vector parallel to the plane. So another way of phrasing this is find a vector perpendicular to the normal vector, right? If it's perpendicular to the normal vector, it's going to be on the plane. It's going to be parallel to the plane. So to figure that out, we need to use the dot product, right? So so we want to find a vector perpendicular to n, and we just said that n was going to be negative I plus 3j plus 2k. Okay. So now I'm trying to figure out a vector v. I don't really know anything about the components, so I'm just going to say, well, I'm going to say the coefficient of that guy is v1i. Coefficient of the second one is v2. Coefficient of the third one is v3. I don't really know what these are yet. But what I do know is when I dot these two, n and v, I should get 0, right? I want to kind of figure out v1, v2, v3 to make this true, right? So n dot v needs to be 0 for this statement in gold to be true. Okay, so let's go ahead and dot them up. So if we do n dot v, we get negative 1 times v1 plus 3 times v2 plus 2 times v3, and we want this to equal 0. And so we just want to figure out a v1, v2, v3 to satisfy this equation. How about, well, if I take v1 to be 3, and I take v2 to be 1, negative 3 plus 3 is 0, and then I could even take v3 to be 0. That would work, right? So if v1 was 3, v2 was 1, v3 was 0, the equation would be satisfied. So my vector that is parallel to the plane, one such vector, there's infinitely many, but one such vector is going to be the vector 3i plus 1, right? That's my v2, 1j, plus 0k, and I don't have to write the 0. So this guy right here is one answer, but again, you could have infinitely many answers for this. Okay, let's look at the next example. We want to find a normal vector to the plane with the equation, with these two equations. All right, so this is pretty straightforward because we know that our normal vector has this form ai plus bj plus ck. And this guy is already in the ABCD form of the plane. So with this first guy, a is 1, right? That's the coefficient of x. B is negative 1, that's the coefficient of y. And C is 2, that's the coefficient of z. So pretty easy answer here. Our answer is going to be A, which is 1i, minus j, so minus 1j, plus 2k. Pretty straightforward there. So that's our answer for part A. For part B, we can do the same thing, except let's go ahead and move the z over so that we're in our form ax plus by plus cz equals d. If I subtract the z over, I get 0.5x plus 1.2y minus z equals 0. And so in this case, a is 0.5, b is 1.2, and c is negative 1. So a normal vector would be 0.5i plus 1.2j minus 1k. So that would be our normal vector for part B, a normal vector. Okay, find a unit vector in R2, which is perpendicular. So R2 is just a fancy way of saying 2 dimensions. And basically what R2 consists of are all of our ordered pairs on the plane, all of the real number ordered pairs on the plane. Now, if you take linear algebra, you're going to be seeing this notation a lot, but yeah, R2 just means 2 dimensions, xy plane. R3 means 3 dimensions, xyz plane. So what we're tasked to do is we want to find a unit vector in 2 dimensions, which is perpendicular to this vector right here. So the first thing we want to do is we want our vector w, or actually let's call it u for unit. We want our unit vector to be a unit vector. We want u to be a unit vector. What does this mean in terms of an equation? How can we say we want vector u to be a unit vector? Like, how could we set up some math to make an equation from that statement? Well, we first have to get our hands on what u looks like. Now, we don't know what u looks like. It's just this random vector that we're trying to find that has these 2 properties. It's a unit vector and it's perpendicular to the vector v. So what I'm going to do is I'm just going to say, well, it's in 2 dimensions, so it's going to have some coefficient u1 attached to I, and it's going to have some other coefficient u2 attached to j. And so that's kind of what it looks like, just an arbitrary unit. Well, we haven't shown that we haven't done anything to show that it's a unit vector or whatever, but that's our vector u. So we're trying to find a u that looks like this. We want it to be a unit vector. If we want it to be a unit vector, what can we say about this here? What does it mean for it to be a unit vector? We want the magnitude to be 1. In other words, we want the magnitude of u to equal 1. Now, what's the magnitude mean? Go back to your notes and look at the definition. The magnitude of u is going to be equal to the square root of the squares of the coefficients. So the coefficients are u1, u2, so we have u1 squared plus u2 squared. And we want this magnitude on the right side of the equal sign to equal 1. We want it to equal 1. So this is an equation that we can use that is useful right here. We're going to put that in our pocket for now. So that's the first criteria. And the second thing that we need to happen is we want it to be perpendicular to v. And what does that mean in terms of algebra? It means that when we dot it with v, we should get 0. Okay? So we want u dot v to equal 0. And we can expand that based on what v is and based on what we define u to be. So u is just u1i plus u2. So when we dot these guys, we're going to take u1, the coefficient of I, times the coefficient of I in v, which is negative 5, plus coefficient of j in u is u2, times coefficient of j in v is 6. And we want this to equal 0. This is just what it means to be perpendicular, for two vectors to be perpendicular. So if we simplify this a little bit, we get negative 5 times u1 plus 6 times u2 is equal to 0. Now you probably know from previous classes that if you have two equations and two unknowns, we have a solvable system. Okay? So how can we figure out what u1 and u2 are just from this equation and this equation? Well, we can isolate one variable and then plug it into the other equation. So like, I think maybe the easiest one to work with is the second one that we found. What we could do is we could add 5u1 to both sides to get 6u2 is equal to 5u1. And then solving for u2, dividing by 6, I get u2 is actually equal to 5/6, the amount of u1. So taking this information and plugging it back up in here for u2, we can get the following. We can get 1 is equal to the square root of u1 squared plus, instead of u2, I'm writing it in terms of u1, which is 5/6 u1 squared. Simplifying this out, I get u1 squared plus 25/36 u1 squared. So this is 36/36 u1, right? It's just 1. So it's going to be, let's see, oh, my mental math, you guys, is really not good. Let me see. You know what? I'm going to get the calculator out. But again, just know that this is 36/36. So when I add these guys, I'm doing 36 plus 25 is 61/36 u1 squared. Now if I square both sides to get rid of the radical, I get 1 equals 61/36 u1 squared. Multiply both sides by 36/61. So you get that, and then I can take the square root of both sides to get u1. And so that's just going to be, that is going to be plus or minus 6/61 is equal to u1. Okay? So then for u2, I can just pick one of these. I'm just going to pick the positive one, but I'm going to go ahead and plug in positive 6/61 in for u1 to get u2. So u2 is 5/6 times 6/61, and that's going to give me 5/61. Okay, so what was I trying to find again? A unit vector that's perpendicular. So I found it. I found the coefficients which defines the unit vector. So my answer is u is equal to u1, 6/61, I plus 5/61 j. And you should verify that this guy, u, is actually perpendicular to this guy right here. And you should also verify that u is a unit vector by taking the magnitude.